Now let's take a moment to connect these filters with some other terms you're likely to encounter. I'm thinking of a two-letter abbreviation that many people use instead of the term filter. Yes, it's got a Q in it, but not the same Q that we've been talking about. Here I'm thinking of EQ, short for, do you know it? Equalization. But what's equal about using filters? Well, it relies on the dated assumption that the only purpose of recording is to faithfully reproduce sounds that happened in the acoustical world. We know better, don't we? Anyway, filters were called equalizers because of the assumption that we would use them to make your recording sound equal to the live sound source. Even the pop music recording industry has come a long way from that, and the album version never sounds like the live, unamplified version. A graphic equalizer is a bank of peak notch filters with predetermined center frequencies and slopes so that they can cover the whole frequency range relatively evenly. They are graphic in the sense that by moving sliders up and down, you can approximate what the resulting frequency response curve would look like. These are common in home and car sound systems, even if they're represented as digital displays rather than using physical sliders. The other kind of EQ you'll encounter is, it starts with the letter P. It's a parametric equalizer. This makes ordinary users tremble because it makes you talk in parameters like the filter type and its frequency and its slope or its bandwidth or resonance or Q. But you know all those things now, right? A parametric equalizer is just one that gives you full control over your filters. So now we've talked about all the filter types, all but one. But first, let me show you something briefly. We started off by talking about the math of things, and I wanted to mention that there are many formulas that can achieve these filtering effects, and you might see things talking in terms of poles or zeros or some fellow named Butterworth or biquad. In general, you don't need to worry about them. They're just different ways of achieving the same types of filters that we've discussed. But briefly, I want you to see the biquad formula. The name is just short for biquadratic, meaning it has two terms that are raised to the power of 2. That's not very meaningful to us, but that's just how the name came up. However, I want you to see that just like a low-pass filter is a running average, pretty simple math, this biquadratic formula is just a little bit more complicated, but it's not bad. Look, it only relies on a few past samples and just does some arithmetic, and it's able to replicate all of these filter types that we've talked about so far, plus 1. What could be left? We've addressed the highs and the lows and anything in between. That would mean it passes all frequencies through equally? Yep. But it still changes the sound in a certain way. What other aspect of sound is there? We've been thinking in terms of frequency and changing each frequency band in terms of amplitude. All-pass filters leave every frequency alone in loudness, but they show us what every kind of filter does to the phase of spectra around center frequency or cutoff frequency. Every filter disrupts phase, and we can't hear it when we're listening to a sound by itself. Phase is only audible when we hear it change or when a sound is combined with other sounds. Focus your attention around where I'm setting the center frequency of this all-pass filter, and notice the faint ripples. That's the sound of spectra around the center frequency being shifted not up and down in frequency, not up and down in loudness, but just in phase, their starting point within their respective waveforms. And we don't hear that exactly, but we hear how they boost and cut their neighboring frequencies differently because of how their peaks and troughs line up. Keep in mind that every filter is doing this. And this is at the root of the advice that you shouldn't apply filters too strongly when you're trying to faithfully reproduce a recorded sound. The general advice is to boost frequencies using a broad bandwidth, cut frequencies using a narrow bandwidth, and keep your boosts and cuts very subtle, usually less than 3 decibels, maybe 6 in an extreme situation. High bandwidth makes the phase disruptions more subtle, as do low amounts of boosting and cutting. And in the case of a notch filter, you're trying to dispel an unruly peak in the frequency spectrum anyway, so phase disruption might help there. So an all-pass filter makes for an illuminating exercise, but it's not useful in music, is it? If we had something that could only affect the phase of a sound, and it's only noticeable when we combine it with other sounds or when we change its center frequency? A guitar pedal, for example, that only changed phase could be called a Now keep in mind that filters can increase the loudness of a sound, so be careful not to cause clipping. Change your individual sound however you need, but then adjust its volume in the mix accordingly. Also remember that resonant filters can add time to the end of a sound, so be sure not to truncate their resonant tails.